if you recall from last 4 lectures on mixed design of concrete, we generally talked about the principles of mixed design, then we looked into several simplified method. In the last lecture of this module, we shall be talking about some recent concepts such as packing density, rheology, and applying them to mixed design principles. So, general outline of our discussion should be packing density, then rheology, followed by the proportioning involving them. Now, you remember that we discussed earlier also, concrete is a particulate system bonded together with particles bonded together, and in fresh state wet, paste and aggregate systems form the concrete, that is in the fresh state. Largest coarse aggregate particles are packed together with interstitial voids, and these interstitial voids are actually filled with smaller coarse aggregate, and the remaining interstitial voids now between the larger size particles of coarse aggregates are filled with fine aggregate. Quite often they could be natural sand or crushed stone, etc., as we have discussed earlier. Now, the further voids which are there within the sand then is filled by cement or cementitious paste or powder and water paste. So, that is what the concrete is, and if we look at it, for example, the same. So, this is your aggregate system, a few of them, let us say, and let us just arrange them in a slightly different manner. We get it, this is the coarse aggregate, they get arranged in this manner. Then the black ones, as you can see, they are the finer aggregate, right. And now the interstitial voids are filled with, so this is the finer of the aggregate system, black ones, and now still gap within will be filled in with some sort of fine aggregate, which in this particular case is sand. And all this put together makes the concrete at the hardened state, which will look like this, So, you see in this one you can see larger size coarse aggregate and the relatively finer, relatively less coarse, smaller coarse aggregates, they go into the interstices, and rest all is filled with mortar system. So, you see the packing of the particulate system, that is very, very important, because if the packing is good, you will require less paste. And we talked about this earlier also, and we talked about the concepts of packing density, if you recollect from module earlier, one of the earlier modules, and we talked about binary mixtures, and we said that if we have two aggregates A and B, we mix in some volume, some proportions of their volume, say A is 1 to 0 and correspondingly B varies from 0 to 1. You remember the void ratios, we said that E A is the void ratio of A and E B is the void ratio of the B, and when you mix them together, theoretically speaking, the void ratios would reduce down as the proportion volume fraction changes, and there is a minimum point, and real situation the void ratio varies in this manner, and but minimum is more or less same corresponding to the straight lines that has been shown, and this is what we have discussed earlier also. Correspondingly, packing density we define as the volume of the solid alone divided by the overall volume, this would increase correspondingly depending upon the fractions of a particular aggregate from pure A to B as we vary pure A to pure B. So, first you have pure A on the left hand side, then you add some amount of B. So, therefore, combination of A and B volume fraction would change when A is 100%, B is 0, and when B is 100%, A is 0, and this is we have discussed earlier, and packing density becomes maximum somewhere in between where void ratio is minimum. The theoretical curve is shown in blue, the real one will be the one shown by black, and this is because of what is called particle interference, loosening effect and wall effect, etc., we discussed. So, this is the situation of binary mixtures, and this can be extended to multinary mixtures, and the volume fraction at which the packing density is maximum or the void ratio is minimum, one can determine from this kind of consideration, and some theoretical models are actually available, and these models of course is not very easy to use because the material properties or aggregate properties that has to be all available. For example, F.D. Lerard, who has actually postulated a number of such models, empirical equations, but a simpler procedure we can actually follow in normal course, in course of mixed proportioning of normal mixtures. So, let us see what are those simpler experimental procedure. Thing is that you pack the aggregate mixture with each aggregate in definite proportions. You can use mass proportions here because it is very difficult to control the volume. So, you use different proportions, mass proportions, and then pack them in a container whose volume is known. Now, this container volume may be V, and one would have to measure this by water replacement method. That means, you fill in this one with water, find out the mass of the water by difference of two weights, empty container and empty container and the container full with water, and this volume is V. Difference of them will give you the mass of water, and from which you can really find out the volume V. Now, then you pack the aggregates in right kind of proportions that you have decided to put in together, and if the total mass is W, or for a given mass it is W, G is the specific gravity, and if it is both force aggregate, their specific gravities would be known same, which could be same. So, the packing density will be simply given by W by G, which gives the volume of the solid, W is the mass of the solid, G is the specific gravity. So, W by G is the volume of the solid divided by V, which is the volume of the container, it will give you the packing density. When you are mixing two of them together, volume of each individual one you can find out, sum total of each individual component divided by the overall volume V will give you, so it can be written as simply, it can be written as W 1 by G 1 plus W 2 divided by G 2, W 2 divided by G 2 1 by V. So, that will be your dP. So, this is how you can find out, it would be W 1 by, for example I'll just rub this off and tell you, this should be actually G, this should be G 2 and 1 by V, that will give you the packing density when you are mixing them up in some definite mass proportions. So, in this manner actually you can find out packing density corresponding to any proportion. Repeat this procedure for different fractions and plot, and such a plot would look like this. Such a plot would typically look like this. For example, here we have got weight fraction S 1 of S 1, a particular, let us say fine aggregate, sand it was, and S 2 is the other one So, as the weight fraction of the S1 increases, the packing density we measured and calculated as I just mentioned, and you find it is maximum at some point, maximum at this point, it is maximum at this point. So, 60% of S1 and 40% of S2 may gives you the highest packing density. So, it is a simple experiment, and you can do this experiment with your you can do this experiment with your aggregates and determine the packing density of any two aggregates, all right, assuming that they belong to a small range of size, all right. So, that is how it is. So, this was the case of example of packing density measurement or measured packing density. So, what you do is, since you have found out 60 and 40 is the best combination, you can choose 60 and 40 and make this as your fine aggregate, and in the case of the fine aggregate example which I talked about. But typically what you will have, normally you will have say you are dealing with 20 mm down coarse aggregate. So, you will have 20 mm down up to 4.75, and then there will be another set of aggregate 10 mm down up to 4.75. This is the two coarse aggregates. Now, find out the best proportions for the maximum packing density of these two coarse aggregates, and let this mixture be M12 for two coarse aggregate. One is MSA 20, another is MSA 10 mm. Now, these proportions, then you mix them up in these these proportions, that is whatever proportion you find out, this is the best which gives you the best packing density, and then use this mixture, right, as one of the aggregate and fine aggregate as another, or if you have more than two fine aggregates, mix them up, find out the best proportion for the highest packing or maximum packing density, choose that proportion of the fine aggregate, choose that fine aggregate, and similarly choose the best coarse aggregate. Normally fine aggregate will be only one, coarse aggregate there may be two. I am talking of normal strength concrete, high strength concrete or other kind of advanced concrete might have somewhat different sort of thing. So, in normal strength concrete 20 mm and 10 mm you will have two different, generally typically in Indian scenario you will have 20 mm and 10 mm two aggregates, you mix them up, find out the proportions of 20 mm and 10 mm for best packing density, and then now use this mixture together with fine aggregate and find out the maximum packing density. That would be the proportions of 20 mm down, 10 mm down, and the fine aggregate which gives you the maximum packing density. If there are more aggregates, you can repeat this procedure for each two. So, consider them binary, each two and two of them, then another two of them, and combine them together. If there are more of them, you can actually go on repeating this procedure, but it would become generally cumbersome if there are too many of them. Typically, you will have two coarse aggregates, one fine aggregate, and using this process you can actually find out what is the best combination of the coarse aggregate, both the fractions mixed together, and the fine aggregate, both the fractions mixed together. So, once you have found out, now we can look into the paste content. So, let us say dP max is the highest maximum packing density. So, 1 minus dP max is the appropriate is the approximate void content in the mix if I mix them. Well, actually void content will be higher, because that is because of wall effect and loosening effect and all that. As we said, when the paste goes inside, it will push the coarse aggregate apart, it will cause some sort of interference in the packing of the coarser aggregate, and therefore, it will cause loosening. Besides that, the paste particles of paste, that is cement etc., will not pack very well close to the boundary of the coarse aggregate. So, you have wall effect and loosening effect, this actually pushes out, which you have discussed earlier. Now, such effect would cause actually dispersion of the coarse aggregate more 3 to 10%, and this also I have mentioned earlier in one of our earlier lectures. So, it means that minimum paste content must account for the above void content, that is 1 minus dP max, and more to account for wall effect and loosening effect. So, 3 to 10% more, that is dispersion is 3 to 10%. So, what you can do is you can actually you can take about 10% more void, you can take about 10% more paste. So, let us go back to the slide again and so 1 minus dP max into 1.1, that should be your minimum paste content in the system, because 10% it will cause dispersion of the coarse aggregate. So, 1 minus dP max into 1.1, 10% more, that will be the minimum paste content. I mean, it could be somewhat less, but conservative way we can start with 1 minus dP max into 1.1, and that is the minimum paste content. So, this is one issue of how much paste you need for to have properly compacted concrete. But the other issue related to this, the consistency of the paste itself. To look at that, we should look at what is expected of the fresh concrete. What we expect of the fresh concrete? Normally, I am talking of again normal concrete, it will contain around 30% void, and it does not conform to the shape of the mold. So, therefore, we compact it by vibration, and when you are compacting with vibration, it stands on a heap. So, it must actually yield easily and move and deform under shear, and shall also flow easily to attain the desired shape. But at the same time, it must maintain its uniformity and cohesiveness. Relative distance between, it must remain uniform. That means, larger size particle should not go at one side, or paste should not move away to another side. So, they should maintain their uniform mixture and cohesiveness. It should look similar, coming from the same source. So, that is what it is. So, that is what should happen. This is what is expected from the fresh concrete. So, we must look into therefore shear stress strain behavior of fresh concrete, because we said that while compacting we apply some kind of vibration, and under the vibration it is actually subjected to a kind of shear stress, and a given particular shear stress it will start moving, and then it will start, in fact, the mobility, the flowing would start, right. So, you can look into this behavior of fresh concrete. Now, if you look at, you see, it has to have flow. Flow of fluid takes place against frictional resistance offered by immediate next layer. If flow is occurring, one layer, you see, if you can consider pipe flowing full, at the boundary velocity is 0, but at the center it is maximum. So, if I consider a small layer in between, the layer closer to the boundary of the pipe will actually exert a kind of frictional resistance to that layer which is closer towards the center. So, in case of liquid flow, this is what happens. Frictional resistance is offered by one layer to the next layer, immediately next layer which is in contact with the moving layer, and there is a velocity gradient normally would be existing, and in case of a laminar flow, in the transverse direction in case of a laminar flow. Now, what is the relevant property? It is viscosity. So, actually shear stress is proportional to velocity gradient, and the constant of proportionality is the viscosity. So, that is in case of liquid. Now, we are talking of concrete or similar sort of thing which is actually in plastic state, and if we recall, we have also talked about that concrete is in plastic state. Now, a solid has got a definite shape and volume, liquid does not have a shape, although it has got a volume. The gas of course, does not have even a definite volume. So, we will confine ourselves to liquid and solid. The plastic is something in between. So, plastic, it does not have, it may have a definite shape, but under stress it would lose that shape, and it will take this, its shape will go on changing. So, therefore, concrete is actually in plastic state. It is not in liquid state, because it is not flowing on its own. Not solid, I am talking of fresh concrete, not solid in the fresh state, because it does not have a definite shape. Once it is hardened, it becomes solidified, I mean solid. Once it sets, it becomes complete solid. Hardening of course is related to strength. So, it becomes solid. So, before it becomes solid, it is in plastic state. So, you got to apply some stress, and when it starts actually deforming. Okay. So, that property is important, and this the subject through which we study this flow behavior of plastic material, we call it rheology. Now, cohesiveness of concrete must be maintained, and it should not segregate, and this property is governed by tensile strength of fresh concrete. If the tensile strength is low, particle will separate out. So, tensile strength is important, and it will be governed by tensile strength of fresh concrete. So, we are looking at rheology, that subject which deals with flow properties, and shear stress for solid. We are just distinguishing the solid. For solid, shear stress is proportional to shear strain, and constant of proportionality is the rigidity modulus. Liquid deforms continuously under shear stress, no matter how small the stress is. Even without the stress, actually it will deform, and shear stress is proportional to viscosity multiplied by shear strain rate. Because I said velocity gradient you can actually express in terms of shear strain rate, and that is Newton law for viscous fluid. Okay. So, essentially tau is proportional to viscosity to dV dy, and dV dy can be written as dx dx by dy, and dx by dy, this can be written as dx dy dt, and this is nothing but shear strain. So, d gamma dt, this can be written as strain rate. So, it will be actually strain rate. So, it is same as so the mu viscosity is the property, but then in case of plastics all this will happen. In case of plastic all this will happen, in case of plastic all this will happen after certain point of load application. In other words, after certain stress has been applied. So, it flows when shear stress is applied. So, the up to certain shear stress it does not actually move, but beyond that it starts moving. So, if I look at this, therefore, if I look at this particular situation, this is for solid, up to this level, up to which actually it will not move, it does not move actually. If it up to certain points it does not move, and beyond this point up to this point it does not move, and beyond this point up to 1 it is actually behaving like a solid. All right, it is behaving like a solid, up to this point it behaves like a solid, this is behaving like a solid. 1 to 2 it started some sort of flowing, and 3 to 4 I mean it is a typical Bingham fluid, not necessarily concrete. So, 3 to 4 it behaves like a liquid, and your velocity profile is like this. So, in a solid there is no velocity profile, velocity is constant here along this direction, velocity here and velocity here everywhere is same. Here the velocity increases, but then there is here again it is constant, and 3 to 4 pure liquid velocity profile is parabolic. So, this is Newtonian liquid for which 3 to 4 behavior is right from the beginning. This is mu rate of strain, shear deformation and shear stress, and Bingham's fluid is 1 up to certain stress it does not show up any movement, no mobility. 1 to 2 it shows this kind of mobility, 2 to 3 it is like this, and 3 to 4 again it behaves like liquid. So, shear stress versus shear strain, rate of shear deformation or shear strain rate is shown, and that is what it is. So, concrete in its plastic state or cement paste in its plastic state can be modeled something similar to this one. And if I extend this line, this point, this is called yield shear stress, this is called yield shear stress, this is called yield shear stress, right. So, if I extend this point is called yield shear stress tau 0. So, this is called yield shear stress tau 0, right. So, two properties are important, tau 0 and this slope. This slope is the mu viscosity. So, Bingham fluid or something similar kind of concrete would show yield shear stress, and then it would show some sort of plastic viscosity. So, these are rheological properties of concrete. If we continue to look at it, we will find that addition of water increases viscosity. So, normal concrete will be somewhere here, addition of water actually causes increase viscosity, I mean increase in the what you call yield shear stress is here, it will lie somewhere there. As you add water, more addition of water, it increases the shear strain rate actually increases. So, liquid Newtonian liquid is somewhere here, addition of superplasticizer or something so or some grain stabilizer or grain, they were somewhere here. So, concrete would be somewhere something like this, this is your Newtonian liquid is somewhere there, all right. So, this is what it is, and if we look further onto this one for concrete, if you add GGBFS or dispersing admixture, viscosity increases in this manner, viscosity, cement dispersing admixtures. So, if I add admixtures, plastic viscosity can increase or decrease, but yield shear stress definitely decreases. So, if I add plasticizer or the water reducing agent, if I add water reducing agent, some of them will increase the plastic viscosity, some of them will reduce the viscosity, but definitely reduce down the yield stress. This is the plastic viscosity. So, if I plot plastic viscosity versus yield shear stress, fine particles like if you add water, they go along this direction, more paste it will also move along this direction, some case of more water, more paste, less water, it actually increases the viscosity, but increases the. So, less water, less reduce water, lower viscosity, lower yield, lower viscosity, sorry, reduce water, less water increases the viscosity, increase as well as increases the tau 0, increase tau 0. So, yield shear stress increases. So, lower water yield shear stress increases, viscosity also increases, and more water you will have lower yield stress, more water goes like this, lower yield stress and lower pressure. Less paste, it actually yield plus viscosity reduces, but the yield shear stress increases. So, what we see is, see more paste, of course, it causes plastic viscosity to increase, and also reduction in the it is along this direction, more paste results in this direction. So, we can see actually if we pulverize fuel ash, it actually reduces your yield shear stress, like reduces the viscosity also, like fly ash or GGBFS. So, what we see, if I add more water, less water, if I reduce the water, actually my plastic viscosity will increase, yield shear stress will increase. Lower paste, viscosity will decrease, but yield shear stress will increase. More water, viscosity decreases, yield shear stress decreases. More paste, if I put in, yield shear stress decreases, but viscosity increases. So, you see I can actually manipulate, because I need least yield stress, least pressure I should be applying before it starts moving, and it must not have too much of friction. So, mu should be as low as possible, mu should be as low as possible, not too much of a friction. So, therefore, you can look into this rheological properties, and therefore, role of paste becomes very important, paste and water, because GGBFS, PFA etc., they also go into paste. Admixture of course has the biggest role in all these issues. So, role of paste we can quickly look into. Water makes the cement paste plastic. By progressive addition of water, air filled voids are occupied by water, and if you recall, I talked about basic water content sometime, which is achieved when all open air voids are isolated by water, right. So, all air bubbles gets actually isolated, and that corresponds to air bubbles becomes isolated within the interstitial space of cement system. Water coats all the cement. So, all open air voids are isolated by water to air bubbles, and this corresponding consistency we call it normal consistency. So, therefore, water in the paste is very important. I must have sufficient water above normal consistency, and if I add higher water content, it makes the paste softer with greater dispersion of cement particles. I should have sufficient paste to fill in the voids, and we have seen that more the paste actually, they of course has some effect on the viscosity, but they reduce down the yield shear stress also. So, I must have sufficient paste in order to disperse the aggregate, that is first thing, and the paste itself should have sufficient water content, so that it is easy to it has ease of flowing. Now, viscosity can be related to dispersion distance between particle, and also they can be related to water cement ratio. Let us see how they are related. Viscosity of cement paste, nu 0 is viscosity of water, delta is a parameter representing distance between particle in micron, 5 micron for water cement ratio of 1.5, and that corresponds to minimum nu. So, you see nu viscosity can be related to water cement ratio and also to some experimental factor B, and water to cement ratio, and N represents for normal consistency, S is Blaine's fineness. So, this S is Blaine's fineness, this is water cement ratio for normal consistency. If you add more water than this, that is the difference, if you add more water than this. So, this term would actually more water, this term will reduce above normal consistency, this term will reduce, and if this reduces, viscosity will actually says first of all Blaine's fineness, finer, viscosity will increase, this term is reduced, viscosity would increase, minus 1 of course is very much there outside the bracket, and if this is actually according to this formula, if this is is very large, lot of water, this term will tend to 0 and viscosity will be nearly 1, which is near to the water. So, whatever it is, this viscosity can be related by through this kind of empirical formula. So, what we understand is it is related to the type of cement of course, but it is also related to water to cement, but we are talking of the cement paste only. Water to cement, how much is the water in the cementitious cement water or powder system, that is what governs the viscosity of the paste itself. In case of concrete, it will be a water content vis-a-vis the total mass or volume of the aggregate and concrete system. So, water content is what would govern this viscosity. So, in concrete, paste forms a matrix where aggregates are dispersed. The matrix separates the aggregate and also holds them together and act as a lubricating material, anabolic plastic deformation. The degree of dispersion is 3 to 10%, that is what we said. So, therefore, decreasing the volume of matrix reduces dispersion and increases particle interference and stiffens the concrete. So, role of paste is very important. Just as by the way, normal concrete, the paste content would be around 30, 32, 33%. If you look at more flowing concrete, it might go to somewhere around 37, 38%. Like self compacting concrete, you have much higher paste, but the paste itself should be flowing, this is very important. So, below a level, lowering volume of matrix should result in harsh and segregating concrete, because aggregate will not be held together, they will move away. And increasing the matrix volume improves the concrete consistency, the matrix itself must be of adequate consistency. So, it increases the consistency. Low water cement ratio matrix, I am talking only of the paste. So, therefore, that is why the water cement ratio comes in. Low water cement ratio matrix may cause dispersion, but cannot hold the aggregate together. So, stiffens. Too high water cement ratio matrix is thin, so water moves out. So, segregation of water, actually bleeding would occur, low dispersion or low holding capacity. So, the proportion of water in the matrix, that is in the paste and powder put together, all kind of cement and other powder put together, that is very, very important, because if it is too high, it may thin and water might run away. If it is too less, then it may not be able to hold the aggregate system. So, the water is the most important aspect. Normal concrete of course have water cement ratio more than 0.26 to 0.33, which is actually normal consistency, thus you will have adequate, paste will have adequate consistency. It is in high strength concrete, you have to look into this. Paste content shall be adequate, not only to fill the voids in the aggregate system, but also more than that required for proper dispersion. For reason of economy and other factors, the paste content is in normal concrete ranges from 28 to 32%, although higher paste content improves the workability, because paste contains cement and that is the costliest material. So, that is why people would have tendency to keep the paste content to its minimal, all right, and mixed proportioning would be done accordingly. So, minimum water content of paste is, that is basic water content we talked about. More water makes and water reducing agent makes flowing paste, mix should have sufficient paste, mix should have sufficient place. This shows a paste, flowing paste, just flowing paste. So, that is what it is. So, water and sufficient paste. Now, paste content, water content and superplasticizer dosage would govern the flow properties of the mix. That is we have understood from our discussion right now. Strength and durability is governed by water to cement ratio or changed water to cementitious plus some Kf, which we have seen earlier, water to binder related to, somewhat related to water to binder ratio. This we have seen earlier, and we can write two equations based on this. How? The equations are like this. First of all, if I am trying to get the mixed proportion, water, volume of water plus volume of the cement must be equals to 1 minus the dP max that I have determined earlier into 10% extra. So, the paste content must be minimum paste content, this is an equation related to minimum paste content, and that is related to packing density. The other equation of relating to water and cement is related to strength, or if I do not know a relationship between strength and water cement ratio, I can start with water to cement ratio required for durability, as we have done in Indian Standard Method practice 10262 2009. So, I can start this as W by C or W by C plus Kf, K you can take as 0.3 to start with, and that must correspond to the durability maximum water cement ratio permissible for durability, or you can take from experience as well, like 10262 method which we have discussed earlier. So, you have a relationship for water cement ratio from durability and strength, and you have another relationship from the packing density and paste content required. So, two equations, water and cement, can be determined. Now, you need to determine the other proportions. From packing density, coarse aggregate 1, what is the fraction of coarse aggregate 1 in the total coarse aggregate system, that was known to me F1 from packing, best packing, optimal packing. Similarly, the fine aggregates or the total coarse aggregate, proportion of coarse aggregate in the total aggregate system, which I can call it F2, is also known from packing density. And lastly, the total volume of aggregate system must be equals to the packing density itself, because volume of the solids, pure solids, that is volume of the coarse aggregate 1, coarse aggregate 2 plus fine aggregate must be equals to the packing packing density, because that is the volume in 1 meter cube. I am talking of all these proportions in 1 meter cube, like we have done earlier, kg per meter cube content of aggregate system. So, I have now 3 more equations and I have 3 more unknowns, WCA1, WCA2 and WFA, fine aggregate content, coarse aggregate content per meter cube of concrete, and coarse aggregate 1 content of per meter cube of concrete. Specific gravities must be the input, like we have done earlier. So, you can see that I have got 5 equations and I have got 5 unknowns, and they can easily be solved. You do not require a big matrix or anything to solve that, you do not require them, because WC can be solved from the previous 2 equations, and these 3 equations will give you simply WCA1, WCA2 and WCA3. So, I have got the mixed proportions of concrete using this constant. So, these 5 unknowns are known to me, and that is the mixed proportion. This mixed proportion obtained would have least flow properties, because I have taken the minimum paste content for given W by C or W by binder. To increase SLUM at maximum possible dosage of compatible WRA determined by mini SLUM test. So, this is the starting point, this was the starting point for workability. It will give you, you measure the SLUM and find out is the right kind of slump you require. If you need more SLUM, well, you can't do without that paste content, because otherwise you will have voids in the system. So, if you need more SLUM, which normally you would, because this will have least SLUM, add possible dosage of compatible water reducing agent, and that should be determined from mini SLUM test. You want to increase SLUM further, add maximum, you will get some SLUM. You want to get more SLUM, you add the paste content and recalculate the whole thing. So, it follows from our earlier discussion of different mix design methods that we talked about. And how do you find out the optimal dosage of the or the compatible superplasticizer or water reducing agent? You do mini SLUM test. Mini SLUM cone looks like this. You can see that it is actually 38 millimeter, 50 millimeter, 19 millimeter, and you have, it looks like this, it is on the platform as shown, and once you have filled it in, lift it almost like our SLUM, find out the SLUM flow. This SLUM flow for the given paste, because water to cement ratio you have determined, water content and cement, water and the cement quantities you have determined, their proportions are known. Mix your cementitious material, it can be extended to all cementitious combination actually, water, cement, fly ash, etc., or cement and water. So, make the paste as you desire for the given water to cement ratio, and add different dosage of water, high range water reducing agent, superplasticizer, hyperplasticizer, whatever you call it, and find out the flow. Now, this flow can be actually measured. So, you can see in this particular example there are 6 such superplasticizer was used to a particular cement system, particular cement plus another cementitious material system. And you can see the flow in centimeter goes on increasing, but there is a point of maximum point, beyond that it is not really increasing. So, this is for superplasticizer 1, 2, 3, 4, 5, 6 superplasticizers have been plotted here. Now, the optimal dosage will be somewhere there for this superplasticizer, optimal dosage will be somewhere, the red one, it will be somewhere here. For each one you can find out what is the optimal dosage. Now, this optimal dose or maximum dose that you can apply, because beyond this by addition of superplasticizer it does not show any further improvement in flow. So, this dose as you have obtained from this experiment of mini SLUM, it should not exceed the limit that has been actually specified by the manufacturer, because then you will have all kind of negative effect. So, if the maximum obtained from here or the maximum dosage specified by the manufacturer, whichever is lower you can put in that, because higher the superplasticizer you are using without any strength loss, segregation or such thing, it would minimize your cement consumption, and that reduces the cost and also adds to sustainability. So, therefore, we should like to use as much as superplasticizer or water reducing as possible to minimize our cement consumption, and find out by mini SLUM method what is the best superplasticizer. The best superplasticizer, most compatible will be one which gives you maximum flow with least dose, right. So, similar kind of test one can determine, and one can determine the particular superplasticizer. Then add this superplasticizer to get the slump you need. If you need still higher slump, then you have to increase the paste content, which means that you will increase water, cement, and correspondingly the superplasticizer dosage also. But the strength calculate, in order to find out whether it satisfies your first trial mix, you have started from, you might start from durability point or from experience as it is done in 10262, which we have discussed earlier and shown as an example earlier also. So, you actually cast trial mix with another water cement ratio, let us say 0.05 less than the durability, or you might still cast another one 0.01 less than the durability. So, 3 water cement ratios or water cementitious ratios as you wish, you might cast for for your control mix, of course, it will be water cement ratio, but if you are using fly ash, then you can either use the DOE method or use the Indian IS 10262 method, whichever way you like, fly ash business you can add. So, you can have 2-3 water cement ratio strength determined at 2-3 water cement ratios to identify what is the water cement ratio you require. So, trial mix will be 2-3, similar to IS 10262, which is quite rational, and check of course the cement content for durability requirement. It should not be less than the cement content specified. This WC-KF for pozzolana can be calculated by as DOE method, earlier we have discussed, or it can also be calculated from 10262 method. So, you see so therefore, complete mixed proportion you can obtain, from the packing density concept, and also using the idea of rheology. As such, today till date it is difficult to model the rheology part from like theoretical understanding of concrete. So, you can apply some basic ideas and obtain your mixed design. Packing density method has been actually proposed, and but as I told you, the parameters required for the aggregate systems are fairly complicated, because the fact you have to determine all those properties of the aggregates or parameters associated with the aggregate if you want to use the formulas which are available. So, but for the normal strength concrete mixes, so one might do it for very high strength system, still one may be doing. So, if you want to do it for normal concrete, then the procedure that has been just mentioned is a good procedure. So, what we have discussed so far? We have discussed packing density concepts, which we have earlier also discussed with reference to aggregate, and we have just tried to show you an example how you can use this concept in normal mixed design practices. If you are doing high strength concrete, then of course, or very high strength system, then this has to be done with much more rigorosity than what has been discussed here. The properties required for each individual type of aggregate, that has to be actually seen and understood and measured. Then we also looked into rheology concepts, namely the rheological properties of concrete, and then we have discussed about how to do mix proportioning using this sort of concept. So, this is not right now still there, is not there in any code or anything of that kind, or any guidelines for practice and so on. So, but one can adopt this sort of practices, especially if one is looking into systematic procedure for development of normal strength concrete, as well as can be extended to the high strength concrete also. So, I think with this actually our discussion on mixed design finished. The summary of this particular lecture is packing, rheology concepts and mixed design. But if we look at the whole module summary, then what we have looked into? First of all, we looked into the basic principles of mixed design. If you recall, we talked about, we had a diagram, and when we say the strength is a function of water cement ratio, most of the mixed design procedure follows that. Then workability or such thing is governed by essentially the aggregate type, their packing, the shape, and so on and so forth, their grading, which is related to the packing density, and etc., etc. And based on the workability and the water cement ratio, we get actually the water content and the cement content, and absolute volume remaining constant, we actually find out the total aggregate content. Fine to coarse aggregate comes from the grading or their packing. So, this is what we discussed in the beginning, followed by Indian standard method, DOE method, British practice, and then we discussed the ACI method. Lastly, today we actually discussed some concepts, modern concepts, and how they can be put into practice in case of mixed design of concrete. So, this completes our module 5, and that ends it. Thank you very much.